Part 2 is calculate the size of the force exerted by one of the wires on the other. And we are given the constant K, which is equal to 2 times 10 to the negative 7 Newton per amp. The way to calculate the size of the force is to use one of the formulas that we've been given to calculate the force between two parallel current conducting wires. And this formula is F equals K current 1, current 2, length of the wire divided by the distance between the wires. So we know the constant K, which has been provided for us, is 2 times 10 to the negative 7. We know the current through both wires, which was provided in the question. It is 10, and it is also 10 for the other wire as well, so they are both 10. The length of the wire is 12 centimeters long, which we will have to convert to meters, which is the metric unit, which is the base unit for distance. 12 centimeters divided by 100 will give you 0.12 meters. So 0.12 meters, and divide all this by the distance between the wires, which was 10 centimeters. Convert to meters, you will get 0.10 meters. So place all that into a calculator. You should get an answer of 2.4 times 10 to the negative 5 newtons. So as you can tell, this is a very, very small number because of how the power of 10 is a negative number. And so this is in the standard form. You can write this in a decimal form, which might be a lot easier to interpret, as 0.0000024 newtons. So you can write it like this in its ordinary or decimal form, or you can write it like this, which is the standard form. As you can see by this answer, it is a very, very small force. So whenever the current flows between these two wires, you're not really going to feel that much of a force. You're not really going to see them move, repel that much. Question C. Consider the arrangement shown in the figure below. Resistor R has a resistance of 6 ohms. So here we have resistor R. And L is equal to 1.20 meter, which is seeing the length of this bar here, which is inside the magnetic field. A uniform magnetic field of strength 2.50 Tesla is directed into the page. So that's the strength of the magnetic field. And as we can see by the directions provided for the magnetic field, it is an X symbol, which means into the page. Now the question is, calculate the speed of the bar as it moves to produce a current of 0.50 amps in the resistor. Let's begin by looking at what exactly we're trying to find. And let's first of all start by trying to interpret what exactly is this diagram doing. What is happening in this diagram? We have a bar here which is being pushed by a force which we call force apply. Whenever we have a conductor that is moving through a magnetic field, a voltage will always be induced across that conductor. What we are asked to do is to calculate the speed if we know that the current that flows through the resistor is 0.5 amps. As you can see by the diagram, the bar is actually connected right here. It is connected here to the resistor. So that means the current 0.5 amps is flowing through the resistor. Now what we can do here is we can find what the voltage is across the resistor. If we know the voltage across the resistor, we also know the voltage that would be induced across the bar. Let's use V equals IR to find what that voltage is. We've been given the resistance of the resistor, which is 6 ohm as shown here in the question. So voltage equals, across the resistor, is equal to the current, which is 0.50 amps, multiply it with the resistance of the resistor, which is 6 ohms. This should give you a voltage across the resistor of 3 volts. Now, this voltage here is not only the voltage dropped across the resistor, but since it is parallel to the bar which is moving, this 3 volts here will also be the voltage that is induced inside the bar. So now we know what the voltage that is induced. We can try to calculate the speed. Now, do we have a formula that relates the voltage and the speed? Indeed we do, and that formula is voltage is equal to the magnetic field strength times the length of the conductor inside the magnetic field times the velocity. So this here is what we're trying to find, the velocity. We know the voltage is 3 volts, we know the magnetic field strength, and we also know the length. So the way to solve this is I will start off by dividing the right hand side by BL, so it'll come to the left hand side and divide into capital V. So this is BL, and that will give me the velocity. So let's plug in a few values. We know the voltage is 3. We know the magnetic field strength, which is 2.5 as given here, and we know the length of the wire in the magnetic field is 1.2 meters. So 3 divided by 2.5 times the length, which is 1.2, will give us the velocity. So we can plug this into our calculator. You will get velocity is equal to 1 meter per second. Therefore, this bar here, in order to produce a voltage of 3 volts, generating a current of 0.5 amps through the resistor, it would have to be pushed at a velocity of 1 meter per second. Here we are at the last question for this section. State Lenz's law. Now Lenz's law is very important, and it states that whenever we have a conductor, let's say we have a conductor right here, and it is being moved into a magnetic field right here. Whenever a conductor is moved through a magnetic field, it will produce its own current. It will have current which will flow. That's if, of course, it is connected, let's say in a loop like that. It will produce a current. Now, we've learned before that whenever we have a current that flows through a conductor, it will produce its own magnetic field. And so it will have a magnetic field around this conductor. This magnetic field here will actually oppose this magnetic field here outside, which induced the current. And so what you will feel as you are pushing the conductor through the magnetic field is a force that's trying to stop you from pushing towards the right. And the reason for this is the conservation of energy. So we cannot create this extra. We cannot just get this current for free. You have to put in work in order to produce that current. And so you have to push a little bit harder to counteract the force which is opposing the motion. So Lenz's law states that induced current produces a magnetic field that will oppose the changes in the magnetic field that produced it. And that is Lenz's law. So we have now reached the end of section 4, or question 4.